Hello, AP Stats class. This is section 13.2, the chi-square test for homogeneity. So our goals for today is to use two-way tables and to perform the chi-square test for homogeneity. So some of the things that you see on the list of goals we've done before, we're basically going to apply them to this new significance test. So in chapter 12, we compare the proportions to two different populations. But what if we had more than two populations? Are we stuck? Of course not. So here's the example we're going to use. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a supermarket compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wine purchased. Here's a table that summarizes the data. Here are the data. You see on the top the different types of music, the three treatments: no music, French music, and Italian music. And on the rows, you see the number of bottles of wine that were purchased for each type of music. So in the very end, you see that how many bottles of wine of each type were purchased. And on the bottom, you see how many bottles of wine were purchased for each of the three types of music. So looking at the conditional distribution, what's the explanatory variable? The explanatory variable was the type of music played. Those are the three treatments: no music, French music, and Italian music. What was the response variable? That was the type of wine purchased. That's what we were measuring. So now we're going to calculate the conditional distributions of the type of wine sold for each treatment. So the first treatment was no music. So out of the 84 bottles of the wine purchased with no music, 30 were French, 11 were Italian, and 43 were other. So you'll see the proportions of each type of wine purchased when there was no music. We're going to do the same with the other two treatments. So for French music, 39 out of 75 bottles purchased were French for 0.52. Italian, only 1 out of 75 bottles were Italian, 0.013, and other was 35 out of 75. For Italian music, 30 out of the 84 bottles were French, 19 out of 84 were Italian, and 35 out of 84 were another. And you can see the decimal proportions for each type of wine, for each type of music. So here's a bar graph displaying the treatment comparing the distributions of type of wine sold. So for each treatment, you see what percentage of the overall total for that treatment was French, Italian, or other. So if we're to compare three population distributions, we would have to do a very complicated test. The null hypothesis would be the distribution of wine types for no music is the same as the distribution of wine types for French music. And we'd also have to test the null hypothesis comparing no music to Italian music, and finally, French music to Italian music. So we'd have to do three significance tests. But if we do many individual tests or construct many confidence intervals, the individual p-values and confidence levels don't really tell us how confident we can be in all three of them taken together. So we can see how one of the treatments interacts with another, but we don't really get to see how all three interact together. So for multiple comparisons, we are going to do a two-part process. First is an overall test to see if there's good evidence of any differences among the parameters that we want to compare. That's the chi-square test we're going to look at today. The second step is a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. This is when we're going to look at the contributions to chi-square, and detailed follow-up analysis is something beyond the scope of this class. So if we are doing multiple comparisons, the null hypothesis would be there is no difference in the distribution of a categorical variable for several populations or treatments, and the alternative is that there is a difference in the distribution of a categorical variable for several populations or treatments. So in this case, our significance test is to compare the null hypothesis, which is there is no difference in the distribution of wine purchases regardless of the treatment. In this case, no music, French music, or Italian music being played, versus the alternative, that there is a difference, that we do believe that the music might, different types of music might correlate to different distributions of wine purchases, whether it's no music, French music, or Italian music. So now to calculate the expected cell counts, we are going to work under the presumption that the null hypothesis is true. Since there were 99 bottles of French wine sold out of the 243, we would expect the proportion of French wine sold under each type of music would be that same proportion, 99 over 243, or 0.407. Since there were 84 bottles of wine bought with no music, we would expect 99 out of those 243, or 0.407, to be French. So that's 99 over 243 times 84 means we expect 34.22 bottles to be French if the proportion of French wines for no music would match the overall proportion of bottles of wine that were French. So to find the expected cell count in any cell for a two-way table when the null hypothesis is true, the expected count is equal to the row total times the column total divided by the table total. Again, the row total times the column total divided by the table total. Now remember, just like with chi-squared goodness of fit, observed counts have to be whole numbers, but the expected counts can be decimals. So once again, here are the observed cell counts. Now to find the expected counts for each cell, we're going to take the row total times the column total and divide it by the table total. So for French wine, you can see those are the expected counts. And often on a table, you're going to put the expected count in parentheses so people can see it, and then you will put them in parentheses on your table so that I'll know that you've found what the expected values are. And again, you're going to need to find all the expected values because the condition requiring the large sample size is going to require you to cite the expected values. So it's a good habit to put the expected counts next to the observed counts, but make sure they are labeled. In this case, I put parentheses around expected, so you should do the same. That way, when I refer to them, or when you refer to them in your answer, they'll be there. So here's the completed table with all the expected counts. Notice each row's expected counts will equal to the total for each row, and the same for the columns. So for the chi-square test of homogeneity, we're going to suppose that the random large sample size and independent conditions are met. The chi-square test for homogeneity tests the null and alternative hypothesis that we saw before. The null, there's no difference in the distribution of categorical variable for several populations of treatments, and alternatively, there is a difference in the distribution of a categorical variable for several populations or treatments. So we will have to find the expected counts for each cell. You're going to take the observed count, subtract the expected, just like you did with chi-squared goodness of fit, square that difference, divide it by expected, and add it up for each cell. Now for degrees of freedom, how do we calculate that? Well, remember, a two-way table has R rows and C columns. Assuming the null hypothesis is true, the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. So df equals R minus 1 times C minus 1. So if it's a 4 by 2 table, the df is going to be 3 times 1, or 3. So the conditions for a chi-square test for homogeneity, the random condition, you need separate random samples, and separate might mean different populations. So again, random samples, plural, or randomized experiment. Like in the example we'll look at with the music, you'll see that there are randomly assigned treatments, or something that you hope to be a randomly assigned treatment. The large sample size condition is the same as it was for goodness of fit. All expected counts have to be at least 5, so make sure you list them somewhere in your response. Finally, you'll need independent observations, and if you have a random experiment, that's going to be satisfied. If you are sampling without replacement, like you normally would be doing, you need to check the 10% condition for each of the samples. So make sure the population size is at least 10 times the size of the sample for all samples that are collected. So again, here are the expected cell counts. So let's take a look at the steps to the chi-square test for homogeneity. The null hypothesis is that there is no difference in the distribution of wine purchase when no music, French music, or Italian music is played. Alternatively, there is a difference in the distribution of wine purchases based on the type of music. This is called the chi-square test for homogeneity. I would strongly discourage you from abbreviating homogeneity, just because. Second step is to check the conditions. So the treatments are randomly assigned, so different times of the day, different customers, who knows, but they were randomly assigned, so we can treat them as a satisfaction of the random condition. Large sample size, if you look at the table, all expected counts, all 9 of them were at least 5. Finally, the independent condition. Now we do have a problem here because most customers aren't necessarily only buying one bottle of wine, because maybe a customer likes a particular style of wine or brand of wine or nationality of wine. So if a customer buys different types, this could be a problem because maybe they already knew what they're going to buy. So this is going to be a proceed with caution situation because we don't really know how independent the purchases are. Because if one customer really likes French wine, he doesn't care what the music's playing, he's going to buy French wine. He might even buy more than one bottle. So the calculations first require to calculate the degrees of freedom. Since this test has 3 columns and 3 rows, df is 3 minus 1 times 3 minus 1, which is 2 times 2 equals 4. The chi-square value is going to be the sum of all the observed minus expected counts squared divided by expected. So just like before, put the first 2 in, add them up, plus dot dot dot, plus the last one, and then find the chi-square. And I'll show you how to do this on the calculator in a moment. So the first thing you need to do before you can use the chi-square test on your calculator is that you actually have to create the two-way table. And to do that, we're going to use the matrix function. So go to your calculator and go to second matrix, and then select edit, and then select matrix A. So that's number 1. You will enter the dimensions of the matrix as 3 by 3. So there you'll see an empty table that looks something like this, and then you'll put in the observed counts from the two-way table. Again, the observed counts into the matrix. So that's what it will look like when you're done using the example we just did. Then we're going to use stat test chi-square test, and we're going to adjust any matrices if necessary. So if you need to change anything, edit it, that's where you do it. Now for the chi-square test, you're going to put in observed, the matrix A, and expected, leave it as matrix B. Now you're wondering, I didn't put in the expected counts. The calculator will output the expected counts into the matrix you select. So the observed matrix will come from matrix A. The expected numbers will be outputted to matrix B. Select calculate or draw. Draw gives you that drawing. Calculate gives you the chi-square value along with the p-value and the df. So to see the expected counts, you need to go back to the matrix menu and you'll select matrix B. Press enter twice, and that's what you'll see. You'll need to scroll to the right to see the remaining expected counts. Obviously, don't write down all the decimal places, just write down a couple. To clear your matrices, it's a little complicated. Sometimes it's probably easier just to overwrite the matrix by changing the dimensions and then just putting in new numbers. But if you really want to clear them all, you can go to the memory menu, which is that second memory, which is the plus key. Select number 2 and then number 5. And you'll see this menu that lists all your matrices. Highlight each matrix and then press delete. To delete it, you won't be asked if you're sure, so once you delete it, it's gone. Now the chi-square test on the calculator, the function does give you the chi-square value as well as the p-value. But if you wanted to use the table, because for whatever reason you wanted to, you can look up your chi-square compared to the df and find which interval your p-value falls in between. So you can see based on this table that the p-value is between 0.01 and 0.0025, and the calculator actually tells you what the actual p-value is. So just like before, the p-value below alpha means you reject the null. So the p-value of 0.00109 is less than the alpha of 0.05. We're going to reject the null in favor of the alternative. There's convincing evidence of a difference in the distribution of wine purchases based on the type of music played. So the second part of doing these procedures is the follow-up analysis. Now, if you take a look at this table, for each of the boxes you see 1, 2, and 3, those are the 3 types of wine. So you have French wine, Italian wine, and other wine. And then the columns represent the treatments: no music, French music, and Italian music. The first row in each block represents the observed count. The second number in each block represents the expected counts. And the third number represents the contribution to chi-square. So if you want to calculate chi-square, you would add up all 9 of these numbers, and that would get you the 18.28. Now, if you notice these numbers, just 2 of the 9 components make up only almost 14 of the 18.28, and that's these 2 numbers right there. So it turns out sales of Italian wine are well below expected when French music was on. When French music was playing, we expected 9.57 bottles of Italian wine to be purchased, but only 1 was purchased, leading to a contribution of chi-square of 7.672. At the same time, when Italian music was on, we saw a lot more bottles of Italian wine purchased. We saw 19 purchased when we expected only 10.72, so almost 100% or 80 or 90% more than what was expected, for a chi-square contribution of 6.404. Remember, you're not just looking at the differences, the numeric difference, you're looking at the relative difference. So for the French, we saw only about 11% or 12% of what we expected. For the Italian music and Italian wine, we saw almost double for what was expected. It's those type of differences that lead to large contributions to chi-square. If you take a look at some of the other numbers, the numbers are big, but because the relative proportion is much smaller, the contribution to chi-square is much less. Now, more advanced methods will provide test and confidence intervals that make analyses more complete. Now that you know where the differences are, you can hone in on what you're looking for and do a more specific or sophisticated test. Finally, our last example is cocaine addiction. You can read the description. Basically, there are 3 treatments. One treatment is desipramine, one's lithium, made famous by the Nirvana song, and a placebo. 1/3 of the subjects were randomly assigned to each of the treatments. So here are the data. You see the groups, and you see how many in each group relapsed. So the 2 steps are to make a graph and then create a 2-way table and do a significance test at the 1% level using evidence. That's basically asking you to do a significance test and showing all the steps. So taking a look at the proportion of relapse by treatment for the first group, the desipramine, 10 out of 24 relapse for about 0.417. The lithium group, 18 out of 24 relapse for 0.75. The placebo group, 20 out of 24 for 0.833. So here's our simple graph. And you can see a much smaller proportion of relapse was in the desipramine group compared to the other 2 groups. The lithium group and placebo group pretty much about the same. So here's a 2-way table. Notice that the rows represent the treatment groups and the columns represent whether or not the patient relapsed. So step 1, we want to test the null hypothesis that there was no difference in actual relapse rates in the 3 treatments. Alternatively, that there is a difference in the actual relapse rate of the 3 treatments, and we're going to do a chi-square test for homogeneity. You can also phrase it as proportion. So if we call P the actual relapse rate for each of the treatments, the null is that all 3 proportions are the same. Alternatively, at least 2 of those proportions are different. So you can frame your hypotheses either way. Most time people just use the words, but if you want to use the symbols, that's fine too. Conditions, you are told the subjects are randomly assigned to one of the 3 groups. For the large sample size, we need to check the expected counts. So let's go ahead and do that. Now, since each row is 24, the expected count for each relapse is 16 because the column is 48. So for all 3 of these columns, the row total of 24 times the column total of 48 divided by the table total of 72 is going to be the same. Turns out the expected count for all 3 of those is 16. Likewise, for the no column, the expected count is going to be 24 times 24 divided by 72, or 8. So those are the expected counts underneath the observed counts. So we verified all expected counts are at least 5. Independence, we have random assignment. And we know that one subject's relapse status shouldn't give any information about the other. But again, because you have a random assignment of treatments, the independence condition is generally satisfied. Doing the calculations, our DF is the row total times the column total, which is 2 times 1 or 2. Here's your chi-square. There are only 6 values, but again, I list the first 2 plus ... and then the last one, observed minus expected squared divided by expected. Gives you a chi-square value of 10.5 and a corresponding p-value of 0.0052. So there's the computer or the calculator display of what you will see after you put the numbers in your matrix and run the chi-square test. So the p-value 0.00502 is much less than 0.01, so we're again going to reject the null in favor of the alternative. There's sufficient evidence of a difference in relapse rates for the 3 treatments. So that's it for section 13.2, the chi-square test for homogeneity. If you have any questions, feel free to ask me or post in the Google Classroom group.